This is just a quick video on the questions we did in class, the stress and strain questions. We did do them in class, so you should have this sheet somewhere plus the workings. This PDF is on Moodle, so it's the ones we did in class 1, 2 and 3. It's all about stress and strain and Young's modulus. This will help you with your assignments, and it will help you with that 6-week assessment period that's due in next week or so. So I'll just go through it. Like I say, the workings out are down here. These are the forms we need. Get that a little bit smaller. Stress strain, the units. So question 1 was all about square bar, 500 mil long, and its cross-sectional area was 12 millimeters by 20 millimeters. Tensile force of 25 kilonewtons. Don't forget, don't do 25 because there's the K there, look. So you need to do 25 times 10 to the 3, which is that, which is the same as 25,000. So don't just do 25, make sure you put the 1,000 on it. And same thing. Stretches by 0.9 of a millimeter. So the change in length is 0.9 of a millimeter. So it's coming out this way, 0.9. 0.9 of a millimeter. Don't forget, we're going to need the area in a bit. So this is the cross-sectional area of that rectangle. It's 12 by 20. So we need to make sure that we convert all our millimeters into meters. So to convert 12 millimeters into a meter, don't forget there's 1,000 millimeters in 1 meter. So to convert 12 millimeters into meter, 12 divided by 1,000 gives you that. You may have to press that perhaps, 0.012 of a meter, or if you press ENG, it changes it into that, 12 times 10 to the 3 meters. So same thing, same thing, same thing. What you can do is, instead of dividing it by 1,000, you can just do this, 12 times 10 to the minus 3. Same thing. Where's that box? Now yeah. We've done the same thing for the 20. So 20 millimeters is 20 divided by 1,000. So I'm going to be using 20 times 10 to the minus 3. 0.02, 0.02. So make sure you convert. 500 mil, we need that in meters as well. So 500 millimeters is half a meter. Or 500 times 10 to the minus 3. 500, 10 to the minus 3 equals half 0.5. So make sure you convert. Then, because we need to work out the stress, we've got to do stress, and we know the stress is force over area. So the area of that rectangle, which is that there, 12 by 20. Don't do 12 by 20, make sure you do 0.12 by 0.02. That'll give you the area in meters squared. So on my calculator I'm doing this, 0.012 times by 0.02 equals. It gives you that, okay, if you press perhaps that, there we are, 240 times 10 to the minus 6. 240 times 10 to the minus 6 square meters. That's our area. So that's part, the cross-sectional area of the bar in meters squared. So we've done that one. Everything in meters, lovely. Stress, now we know stress is force over area. We know the force and we know the area. So 25,000 divided by, let's put that in a bracket perhaps, 240 times 10 to the minus 6, close brackets, equals. So there's our answer. There's nothing wrong with that answer. You could write all that down if you want to. Right, make sure you get all the numbers in. Or you could press ENG to get that, like I've got there. Look, I've rounded up a bit, so okay. or we know that 10 to the 6 is mega, so we know that 10 to the 6 is a mega, so I put megapascals in there. There's nothing wrong with that answer, there's nothing wrong with that answer, and there's nothing wrong really with that answer. Pascals, get the unit in, right? That's our stress. It's always big, stress, always big. Next thing we know is strain. We know strain is change in length over original length. The change in length is 0.9 of a millimeter. 0.9 of a millimeter. And its original length is 500 mil. So, change in length over original length. So I've kept this in millimeters. With strain, because it's a length over length, as long as they're both in the same units, it's the same difference. So I've kept them in millimeters. 0.9 divided by 500 gives me the strain. 1.8 times 10 to the minus 3. There's no units for strain, it's a length over length. I mean, you could, if you wanted to as well, convert them into meters, but just to show you get the same answer. So 0.9 of a millimeter, which is going to be that much of a meter. 0.9 divided by 1000. Divide that by 500 millimeters in a meter, which is going to be that. Plus equals gives me the same answer. As long as they're both in the same unit, you can be in miles, kilometers. Okay, perhaps it's best if you get into the habit of converting into meters, but as long as they're both in millimeters or both in meters, it's a length over length. That's our strain, very small strain. And I think the last part was to work out Young's modulus, or the elastic modulus. And we know that Young's modulus is stress over strain. We know the stress and we know the strain from previous parts of the question. So to work that out, 104.17 times 10 to the 6 equals all that. Obviously I'm rounding up there, I'm rounding up a bit. Divide by the strain, 1.8 times 10 to the minus 3 equals 5.7. Okay, we don't like the 10 because there's no symbol for 10. Press ENG, puts it into 9, 369, 57.87 times 10 to the 9 pascals, or 57.87 gigapascals. So that's question 1. Question 1's done. No trick there. Question 2 is very, very similar question 2, but we've got a round bar with a diameter. So it's got 100 mil long, it extends by that much, and it's 30 kilonewtons. So same thing, area of the tube, stress, strain, and Young's modulus. So question 2, this one, it's a round bar, so the cross-sectional area is going to be this area here, this circle. We know it's 1000 mil long, which is 1 meter. So don't forget, we need to work out first of all the area of this circle, the cross-sectional area. We know it's 12 mil diameter. I'll convert that into, I'll convert that into a meter. So 12 divided by 1000 gets into meters. 0.012 or 12 times 10 to the minus 3. That's our diameter. We know we've got a force of 30 kilonewtons and it stretches by 0.79. 30 kilonewtons, don't forget, 30 times 10 to the 3 kilo. So it's 30,000 newtons. First of all, work out the area. If you want to, you can use pi r squared. Some people don't like to use pi r squared because you can't really measure a radius. You can measure diameter quite easily. But if you want to use pi r squared, don't forget radius is half, so you need to divide that by 2. So that's why I've got 0.006, because it's pi r squared, where r is the radius. So all I've done there, I've done this 0.012, that's the diameter in meters, divided by 2 radius. There's my radius, 6 times 10 to the minus 3. 1, 2, 3. So that's my radius. If I square that and times it by shift pi, I get, that's my area. Don't like 10 to the minus 4, press ENG, 113. I round it up a bit, 10 to the minus 6 meters squared. So that's a cross-sectional area in meters squared. That's the pi r squared way. You can also do pi d squared over 4. Saves you converting that into radius. Get the same answer. Obviously the diameter is 0.012. Square that, times it by shift pi equals that. Divided by 4, divided by 4 equals. Again, press ENG because there's no symbol for minus 4. 113 to the minus 6 meters squared. So that's the round bar. Once you've got that, it's the same thing as before. It's the same thing as before. We've got stress, force over area. We know the force, we know the area. Make sure you put in 30 kilonewtons. 30 kilonewtons. Divide by the area, which was this. Rounding up a bit. 113.1 times 10 to the minus 6. Don't forget, stress is force over area. It's going to be a big number. Press that. You can put that number in if you want to. Put that number in. Or you can press that. 10 to the 6. Nothing wrong with that. Obviously, I've rounded up a bit. 10 to the 6. Or megapascals. Correct. Correct. And the final one was to work out strain. So we know that it's stretched by 0.79 of a millimeter. And it's 1,000 mil long. So again, I'll stick in millimeters. So change in length 0.79 over 1,000 millimeter. 0.79 divided by 1,000 obviously will give us that. That's our strain. Very small, very small. If you want to convert that into meters, so we'll do that in meters. So 0.79 of a millimeter. If I divide that by 1,000, I get in meters. And obviously that's going to be 1. 1,000 millimeters is 1 meter. So I'll just do it. 79 over 1,000. Nothing wrong with that answer. Or that. So it's the same thing. It's a length over length. As long as they're both in the same unit, you're laughing. No units. No units. It's a length over length. Classic writing. Right. No units for strain. And then just like before, next one, Young's modulus. Stress over strain for Young's modulus. Elastic modulus or Young's modulus. Stress over strain. That's my stress. That's my strain. Again, it's going to be big. Going to be big. Young's modulus is going to be big. So we'll do 265.25 to the 6. Divide by 790, 790 minus 6. Close the bracket flaps. There's the number. Okay. Don't like the 11. Press ENG. Gives us into 9. 335.8. So I've done a bit of rounding there perhaps. 10 to the 9. Right, nothing wrong with that. Tick. Or you could do giga, because giga is 9, so 335 gigapascals. Nothing wrong with that. Question 2 done. Nothing hard there really, apart from making sure you got the area correct. The last one was again very, very similar to the first one. Square bar, 19 by 25, 400 mil. 35 kilonewtons. and it's been squashed by 1.2 mil. At the moment we'll use that as a positive number, but obviously if you're squashing something it's changing length, so in future sums it'll be a minus number because it's compression rather than tension. Tension's expanding, compression squashing. But it's the same thing, convert everything into meters. Convert all your lengths into meters first. 19 divided by 1000. Right? Convert 25 into meters. Convert the 400 into meters. So 19 divided by 1000. Or just 19 times 10 to the minus 3. So 19 times 10 to the minus 3. Same thing, saves you doing that bit there, I suppose. We know we're going to find the stress, so we need the area first. It's a square or a rectangle, so 19 by 25. So 19 times 10 to the minus 3. Don't forget we need to be in meters, so 19 times 10 to the minus 3 times by 25 times 10 to the minus 3 will give us our area in meters squared. So press E and G, so 475 times 10 to the minus 6 meters squared. So it's got to be meters. We now know that force over area is stress. So there's our force, there's our area. Same as before, so 35 kilonewtons, kilo is 3. Divide by the area, I'll put in bracket 475 times 10 to the minus 6. Gives me my stress, it's going to be a big number. Nothing wrong with that, you can put that in if you want to, or you can put that in 73.68 times 10 to the 6, or mega. Tip 2. Strain, change in length over original length. Again, it's been squashed by 1.2 meters. It's 400 mil long. I've kept everything in millimeters, as long as they're both the same units with strain. So 1.2 divided by 400 gives us our strain. It's going to be small, no units. 3 times 10 to the minus 3. That is in compression, so that there really is a negative number because it's going that way, whereas tension's going that way perhaps. So when we do thermal, we'll consider this as a minus number, but for now we leave it like that. 3 times 10 to the minus 3, that's the strain. On the last one then, also upside down. I have to turn your heads a bit, but stress over strain is Young's modulus. So there's my stress, and there's my strain upside down. Gives me Young's modulus, big number. So I'll read upside down, 73.68 times 10 to the 6 divided by the strain, which was small, 3 times 10 to the minus 3, gives us 2. There we are. Don't like the 10, press engineering. 4.56 10 to the 9. 10 to the 9 there, look. Or gigapascal. Nothing wrong with that answer. Nothing wrong with that answer. So that's the Young's modulus. So 3 questions, all on the same thing really: stress, strain, and Young's modulus. Make sure you get everything into meters. Don't forget with strain, as long as the strain is in the same units, doesn't really matter. But when you're doing stress, make sure everything's in meters squared, because the SI unit of length is really meters squared. Hope that helps. See you later on.